So this is section 6.3, medians and altitudes of triangles. We will start by defining what a median is. A median is a segment that goes from the vertex of a triangle to the midpoint of the side opposite of a triangle. And if you draw all three of the medians in a triangle, they will meet at a point of concurrency, and we call that point of concurrency a centroid when it is the result of medians in a triangle. Now, the centroid has a property, and that's what the centroid theorem is telling us about, that the centroid of a triangle is 2/3 of the distance from each vertex to the midpoint of the opposite side. So what does that mean? If we look at this graph, that means from B to F, that's the whole median. But if we go from the vertex to the centroid, BP is equal to 2/3 of the median. So from the vertex to the centroid is 2/3. So BP is 2/3 the length of BF. Well, if BP is 2/3, then how much is PF? Hopefully you said 1/3, because 2/3 and 1/3 makes 3/3, which is one whole. So we can say that PF is equal to 1/3 the length of the median, which is BF. Can you make a relationship between these two parts of the median? So PF is the part from the base to the centroid. BF is the part from the vertex to the centroid. Hopefully you see that BP is equal to 2 times PF, because 2 times 1/3 is 2/3. So we should see that they are related to each other by a factor of 2. And you have to be able to play around with these numbers, and they'll help you to solve different problems involving centroids and lengths or portions of the lengths of the medians. So our first example is a numeric example. It says in triangle RST, point Q is a centroid, and they're telling us that SQ is 8. So the first thing you should notice is say, well, Q is a centroid, and SQ is the distance from the vertex to the centroid. So hopefully you say that's 2/3 of the median. What segment is the median in this part that I've highlighted? Well, you would say that's SW. So SW is equal to I have that backwards. SQ is equal to 2/3 of SW. SQ is equal to 2/3 of SW. And again, this is the whole median. And this is the segment from the centroid to the vertex. And to solve this, we want to get rid of that 2/3. What do we need to multiply 2/3 by to eliminate it? Hopefully you say 3/2. So if we multiply by 3/2, we should see the 3's and 2's will cancel. But anything you do to one side of an equation, you need to do the same thing to the other side of the equation. And now we can say, let's plug in the 8 for SQ. And we have 3/2 times 8, and these will cancel and leave us with SW. 3 times 8 is 24/2 equals SW. 12 is equal to SW. That is the length of the median. Now they also want us to find QW. Well, 8 plus QW is equal to the whole median, which is 12. Subtract 8 from both sides, and QW is 4. Or, as we said on the previous page, the portion of the median from the base to the centroid is 1/3 of the median. So that means it is 1/3 of SW, and we just found that SW was 12, so 1/3 of 12 is 4. So we have multiple ways we can solve for this once we get an understanding of the relationship between the centroid and how it partitions the median. So here's another problem with the centroid, but it introduces some algebra to it instead. Given that Z is the centroid in the triangle ABC, and that AZ is x plus 7, and that AY, this is the whole median, is 9x minus 27. Well, let's first write the equation using the names of the segments, and then we'll substitute in. This will ensure that we plug everything in correctly and we distribute properly. So AY is the whole median, and AZ is the segment from the vertex to the centroid of that median. So we should remember that AZ is equal to 2/3 of AY. Now let's plug into each of these with their algebraic expressions. AZ is x plus 7, and that equals 2/3, and AY is 9x minus 27. And when we distribute this 2/3 through here, we get x plus 7 is equal to 2/3 times 9x minus 2/3 times 27. So 3 divides into 9 and gives us 3. Multiplied by 2, we're at 6x. And 3 divides into 27, that gives us 9. Multiplied by -2 is minus 18. And we can subtract x from both sides and add 18 to both sides. And that gives us 25 is equal to 5x, or that x is equal to 5. The problem, though, says find the length of ZY. So we want to know the length of ZY. So to do that, we should first find the length of AY. AY is equal to 9 times 5 minus 27. So it is 18. And if you recall, we said the distance from the base to the centroid is 1/3 the entire median. So we can say that ZY is equal to 1/3 of AY, and 1/3 of 18 is 6. So there is our algebraic example with medians and centroids. Here's another one. You can pause the video here, try to work it out on your own. Once you've got your answer, unpause the video and see if you get the same result I have. Given that Z is the centroid of the triangle and XZ, well, here's our XZ. That is x plus 10. I see that's going from the base to the centroid. So this is 1/3 of the median. And then they give us BX. Well, BX is the entire median. So again, I recommend writing your equation with the segment names. So we have that xz is equal to 1/3 bx, and then we can substitute in our algebra. X plus 10 goes in place of xz, and then we have 1/3, and bx gets replaced with 15x minus 18. And when we distribute this 1/3 through, we should have x plus 10 is equal to 5x minus 6. Let's subtract x from both sides and add 6 to both sides. 16 is equal to 4x, or 4 is equal to x. And it says find the length of BZ. BZ is the distance from the centroid to the vertex of the median. We should recall that is 2/3 of the median length. So BZ is equal to 2/3 the length of BX. We should use this x equals 4 to find BX. So BX is equal to 15 times 4 minus 18. $42. So if BX is 42, then BZ is equal to 2/3 of 42. Two divided by 3 times 42 gives us 28. And there is our answer for BZ. Next, we can find the centroid of a triangle in the graphing plane. So if we were to graph these points, 2, 1 is R, 5, 8 is S, and 8, 3 is T. So the centroid is equal to the average of the x and y coordinates. So it's going to be 2 plus 5 plus 8 divided by 3, comma, 1 plus 8 plus 3 divided by 3. So basically I took all of the x coordinates and added them up and divided by 3, and I did the same thing with the y coordinates. So that gives us 2 plus 5 plus 8 is 15. 15 divided by 3 is 5. And then 1 plus 8 plus 3 is 12. 12 divided by 3 is 4. If we go to 5, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, there's our centroid. And that would be the point that all of the medians intersect at. And again, that centroid would be 2/3 the distance from the vertex and 1/3 from the base for the length of the median, if we were to draw this median in here, or this median, or this median. So that's all they asked us to do, is find a centroid for this one, but we have a quick and easy way to calculate the coordinates of a centroid. Add up all the x's, divide by 3, add up all the y's, divide by 3, and you're done. Next is the altitudes. An altitude of a triangle is the perpendicular segment from the vertex to the opposite side, or, and this or is important, to the line that contains the opposite side. And that or has to do with obtuse triangles. So if you have an acute triangle, the altitude is inside of the triangle. If you have a right triangle, then the altitude is one of the legs of the right triangle. And if you have an obtuse triangle, well, the altitude is outside of the triangle. Here is my obtuse triangle. And they had to extend the one side, and that's why it says or, to a line that contains the opposite side. So this line contains the opposite side of the triangle, but it is outside of it, and we can still measure the height. The height is the distance from the base to the vertex. So we see that this can be measured even though it is outside the triangle. The orthocenter is where all of the altitudes intersect. And again, this will be different for right triangles versus obtuse triangles, where the orthocenter will be outside the triangle or on the triangle, as we've seen with the perpendicular bisectors. So they're showing us that in this image here. So again, this is the obtuse triangle, and you see that the orthocenter is outside, and here is the right triangle, and the orthocenter is on the triangle itself, and the acute triangle has it on the interior. So here is the concept summary. These are the different special segments that exist in each of the triangles, and these are the point of concurrency that exist when you draw three of them in a triangle, and here are the properties for each of those special points of concurrency. Again, remember, a circumcenter is equidistant from the vertices, so we can draw a circle that goes through the vertices. The incenter is equidistant from the sides, so we can draw a circle that touches all the sides from the interior. The centroid is 2/3 the distance from the vertex and 1/3 the distance from the base for that median it's on. And the lines containing the altitudes of a triangle are concurrent at the orthocenter. There's no special property that we would use it for. It was just a special triangle segment, so we discuss how to find it and what its name is, but it doesn't have any of the special attributes that the circumcenter, the incenter, or the centroid have. So that's the end of the lecture. Go to the Practice A and Practice B worksheets. Apply these properties of the median and the altitude, and then check your answers with the answer key.